In this video, we're going to look at the ideal gas law, often affectionately referred to as PIV-NERD. And before we get there, we're going to recap a little bit what we talked about, the combined gas law. So the combined gas law uses these three relationships, these historical gas laws that relate pressure, volume, and temperature. And each of those three laws will keep one of those values constant. So the middle one there, Boyle's law, for instance, is the relationship between pressure and volume at constant temperature. We decided if we didn't want to keep one of them constant, we could smash them all together into this one expression, P1V1 over T1 equals P2V2 over T2. Essentially what we're saying is that relationship between pressure, volume, and temperature, PV over T, will always equal a constant value. Now, of course, we are still keeping something constant, and that's the amount of gas we're working with. And so what if we don't want to keep the amount of gas or the number of particles, which in chemistry we refer to as N, which stands for the number of moles? What if we don't want to keep that constant? Well, the guy that helped us sort that out was Avogadro. And of course, we remember Avogadro from Avogadro's number, 6.622 times 10 to the 23rd particles in a mole. And Avogadro, in part, came to that hypothesis through came to that realization that the number of particles in the mole would have to be constant through his hypothesis that equal volumes of gas at the same temperature and pressure contain the same number of particles. This is a simple but super useful idea. And so what we're saying is, if volume is the amount of space that particles have to move around in, if temperature is how fast they're moving, and pressure is the number of collisions, well then, if we have two boxes of the exact same size, and all of the particles are moving at the same speed, and the number of collisions is constant, the only way that would be the case is if the number of particles were the same. Because if you had two containers the same size, particles moving at the same temperature, and one of them had more collisions, well, then the only explanation for that would be that that particle at higher pressure had more, or that, sorry, container at higher pressure had more particles. And so we get the relationship from Avogadro relating volume and number of particles. So if you double the volume of a container and yet you're keeping the speed of the particles and the collisions the same, well, you better double your number of particles in order to get there. All right, so let's put all of these things together. So this is not the combined gas law per se, but we are going to in fact combine all of those relationships. And if we think about the idea that volume over temperature at constant number of moles and constant number of pressures will always be equal to a constant we'll call C1. The same thing, holding the appropriate variables constant, P times V is equal to another constant C2. And Avogadro's hypothesis says that volume over moles at constant P and T is equal to another constant C4. Apparently I've gone a little bit out of order in my animation here, but it should all work out. And the pressure temperature relationship is C3. And if we, again, combine all those things together, then we get this relationship, PV over TN. I don't like that this image uses a capital N there. It should be a lowercase n, but I like the image, so we'll stick with it. So Gay-Lussac, Boyle, Charles' law, Avogadro's hypothesis, all of those things are equal to a single constant, which we're going to call KB, and we can get rid of the rest of that clutter. And this expression here, we're going to refer to as the ideal gas law, where the constant KB usually isn't listed as K, it's usually listed as R, which is referred to as the ideal gas constant. And then we often rearrange this equation to give us PV equals nRT, which is where we got our PIV-NERD at the very beginning of this. So pressure and volume equal the number of moles times R, which is the ideal gas constant, times the temperature. So again, R is equal to the ideal gas constant. Its value is always the same, but the number varies on the units you choose to use. Think about all of those different pressure units that we talked about. So this is using pressures of kPa, liters, Kelvin, and moles. That value is 8.31. instead of liters, we could use gallons or ounces. Instead of kilopascals, we could use millimeters of mercury instead of Kelvin. You can't use degrees Celsius, so you have to be in an absolute temperature scale here. So your temperature options are Kelvin or Rankine. Moles is usually pretty constant. Otherwise, if you change that to some other measure of the number of particles, I mean, I guess we could change it to individual particles, but if you start measuring your quantity by grams, then your constant becomes specific for a particular substance. Again, kPa could be other values, liters could be other values. Another value that is commonly used for R relies on that atmosphere label for pressure, and so 0.0821 liters atmospheres over Kelvin moles, and there are a number of different values. These are probably the two most common used in introductory chemistry textbooks. So let's talk about how that would work. So we talked a while back about collecting gases during experimental processes, and that if you have a container of water, you invert it in a trough of water, you fill that thing, you begin to fill that thing with gas, and it will displace the water. And if your jar there on the right side that you're bubbling the gas into has volume markers on it, we can actually measure how much gas we're collecting. So that's how you would figure out volume. Pressure is a little trickier, but if you have a barometer in the room, you can certainly measure the pressure of the gas. And then the temperature, we could assume that the gas bubbling through that water is going to exchange heat with the water, and that if you just stuck a thermometer in that trough, you get a pretty good estimation of the temperature. So it's really, really difficult to count the number of particles, to know how many moles you have. It's fairly easy to measure pressure, volume, and temperature, and that's one of the things that makes the ideal gas law super useful. So here we have a sample of hydrogen. We've bubbled it into that jar, and we've measured it out at 8.56 liters. That apparently is a pretty darn big jar there. We have a temperature of 28.1 degrees Celsius, again, probably the temperature of the water bath, and the pressure of 1140 millimeters of mercury. And so it says determine the number of moles of hydrogen in the flask. And so again, this is a really good example of kind of the usefulness of the ideal gas law, in that you can take macroscopic values that are easy to measure, and you can then use those to calculate a quantity of particles which would be impossible to directly measure. So you're having to measure those indirectly. That R, of course, is 8.31 kPa liters over Kelvin moles. It's a constant. It will always be that value. So let's talk about plugging into the ideal gas law equation to solve for this value N. Well, the first thing we have to do is get our values in the right units. Since our R is in kilopascals, we're going to have to convert that pressure to kilopascals. And you're going to do that using your standard pressure values. So set yourself up a game board, use your standard pressures as your ratios, and go ahead and pause the video, see if you can convert millimeters of mercury into kilopascals. So if you weren't sure what to do, what you're doing is you're setting up your game board. As always, we put our given piece of information in the top left, and your standard pressure values then become your conversion factors. We want the millimeters of mercury on top, kilopascals on the bottom, and we go to our list of standard pressures. 760 millimeters of mercury is equal to 101.3 kilopascals, and that gets us 151.95 kilopascals. Notice I have not rounded my number off to three significant figures, but I have underlined that value so I know where that number should be rounded off. And then our temperatures in degrees Celsius, we need to get that into Kelvin, so you're going to add 273.15, and then go ahead and plug those things into the PV equals nRT. Again, I encourage you, go ahead and pause the video, plug them into the equation, see if you can solve for N, and then check your answer. If you're not sure what to do, just hold on 1 second and we'll roll through the calculation. Okay, so here's the setup. Pressure and volume are on the left. N times our constant, 8.31, times 301.25. So that's the 28.1 plus 273.15. And again, I did not round that value off yet, but I did underline where I should have rounded it off. We're going to need to get the n by itself, so we're going to move those other two values to the other side of the equation by dividing. And that gives you this expression here. So I want you to notice the units that cancel out in this case. The Ks are going to cancel out, the kilopascals are going to cancel out, the liters are going to cancel out. And let's think of what we have for our units now. We're dividing by a unit that has a fraction, and what we're left with is 1 over moles in the denominator. But if you remember your algebra, dividing by a fraction, dividing by 1 over moles, is the same thing as multiplying by the reciprocal, which is moles over 1. That means our final unit here is moles. So you're going to multiply across the top, you're going to divide across the bottom. You're going to round for sig digs. If you didn't already work all the way through the problem, you might take a look at what we have and plug it into your calculator and see if you get the answer that I get. Go ahead and pause the video to do that. And so you should have gotten 0.519 moles of hydrogen gas, and that's how the ideal gas law works. So I'm going to leave you with this question: combine or ideal? How do you know which equation to use? Well, it's fairly simple. PV equals nRT of the ideal gas law will help you solve a problem when you have one set of conditions, and it's usually I have 3 values that I'm able to measure, I have 1 value I'm not. So you will be given everything except 1 value, and you have to solve for it. Combined gas law is for a changing set of conditions. I start with an initial pressure, volume, and temperature, and I change the volume or the temperature, and I want to know what happens to the pressure. Again, you can get back to the individual gas laws. If anything is held constant, you just cancel it out. So if your volume is held constant, V1 and V2 just go away, and you're left with P1 over T1 equals P2 over T2, and you'll solve for whatever your unknown is. And that's the ideal gas law.